But even before that, I introduced to you what stationary points actually are. So for stationary points, there are mainly three different types. You have your maximum point, you have your minimum, as well as your point of inflection. Okay, to find out what are the coordinates of all these 3 points, one very critical feature of a stationary point is that your dy over dx at that particular point will be equals to 0. Okay, because the tangent is such that the gradient is actually equals to 0. The tangent itself is horizontal to the x-axis. Okay, then in order to determine the nature of these 3 points, okay, or the stationary points itself, that means either is it maximum, minimum, or point of inflection, we have learned that we can use first derivative test, okay, to determine the so-called nature. Right, I realized yesterday that I forgot to mention, okay, and emphasize what nature of stationary points mean. It means that if I have the coordinates of the stationary point, I need to know the nature, meaning to say, is it maximum, minimum, or point of inflection? Okay, for first derivative test itself, we usually have to draw in our table, or rather, we always have to draw our table, okay, to find out x, and then after that, your sign of your dy over dx, as well as the sketch of the tangent. Okay, so if you're looking at the point AB, for example, our x value will be a minus, and a plus over here. Okay, such that it will help us to determine your nature of the stationary point. Okay, so looking at try 3. Okay, we are given in this case y equals to x cubed minus 1 squared minus 3. We want to find out what is dy over dx first. That would be to do our usual differentiation. So we apply our chain rule and we arrive at this. Okay, so bring down the power, then x cubed minus 1 power minus 1, and then differentiating your x cubed as well. So we get 3x squared. Okay, you can simplify it such that we get 6x squared times x cubed minus 1. It's not necessary for us to fully expand it, but if you want to, you can. Okay. Determine the nature of all the stationary points of the curve. And we know that stationary points are such that dy over dx is equals to 0. So therefore, 6x squared times x cubed minus 1 needs to be equals to 0. Okay? So if you have the tendency, okay, to divide variables, meaning to say in this case, it will be your x. Okay, if you have a tendency to, let's say, cancel out your x, right? Okay, then that's dangerous because you need to recognize in this particular case, when 6x squared times x cubed minus 1 is equals to 0, this means that 6x squared is equals to 0 or x cubed minus 1 equals to 0. Okay, that's your zero product. Right? Such that you will realize that x is equals to 0 here. Otherwise, x cubed equals to 1 and x equals to 1 itself. Okay. So finding out the x coordinates already, we proceed to find out the y coordinates. Okay, therefore we have two coordinates of two stationary points, 0, -2 and 1, -3. Okay. And then at 0, -2, we set up our table to make use of the first derivative test. Okay. So in this case, the middle will be 0. On the left will be 0 minus 0 plus. That means we look for 0 minus away 0.1. So we look at when x is equals to -0.1, and over here 0.1, positive 0.1 itself. Okay. Then we substitute it into your dy over dx to figure out what is the sign of the dy over dx. Okay. So could you give that a try now? Right, for the point 0, -2 as well as the point 1, -3. Okay, give you about 2 minutes to work on it. Figure out what is the nature of that stationary point. Okay.
just now asked me a good question. Okay, he asked, is it necessary for us to determine the y coordinate? Okay, over here, when we actually only need the x value to determine the nature. Okay, my answer to him is that we need to find the coordinates, because if I don't have the coordinates over here of the stationary point, okay, then what are we to say that
this particular point has this nature itself. Okay, so you need to have the complete sensing of the coordinates of that point before we talk about the nature. You cannot just say that x equals to something and then say that the nature of that particular point is actually going to be maximum, minimum, or point of inflection. Okay, so with this, I hope that you have managed to figure out, okay, that the sign in this particular case should be negative, negative. So your sketch looks like this, and therefore your 0, negative 2 is a point of inflection. Okay, so point of inflection, if you recall, yesterday we mentioned that, okay, it can either be negative, negative, otherwise positive, positive. Okay, so point of inflection, there's no change of sign. Okay. Then for 1, negative 3, what you should get is a negative sign over here and a positive sign. So your graph, your sketch of the tangents look like this, and your 1, negative 3 is a minimum point. Okay, so that is our first derivative test, okay, to help us to determine the nature. Alright, now I'm going to introduce to you the second derivative test. For the second derivative test, you might find that it is easier, more straightforward to use. However, there are limitations to the second derivative test. Okay, so let me just explain what the second derivative test is. We are going to be looking at this thing called d square y over dx square, d2y over dx square. Okay, sorry, usually we say d2y over dx square. Okay, so that is your second derivative. By second derivative, what we're saying is that with the dy over dx that we have already found, okay, we differentiate one more time. Okay, that's why it's a second derivative. Okay, differentiate another one more time. So for example, if let's say y is equals to x minus 1 square, okay, then your dy over dx will be 2x minus 1, okay, and then this simplifies to be 2x minus 2, and then your second derivative, differentiating this, you will get the value. Okay, so that is what we mean by second derivative. In this test itself, okay, we're looking at whether is it negative or is it positive. Okay. So when it is negative, it points to us that the nature of that particular point, okay, will actually be minimum. Okay, so when the second derivative is less than 0, at the value where x is equals to that particular point, okay, your AB is a minimum point. It's maximum, sorry. Okay, so how do I go about remembering this? Okay, while it is not mathematically, conceptually, it doesn't rely on the math concept itself. Okay, but how I remember is that your second derivative less than 0, we always think that less than 0 is a set base, right? Remember the coefficient of your x square quadratic graph. Okay, if it's less than 0, it's a set base. Okay, that gives you a maximum point. Okay. So that's how I remember this thing itself. Okay. Then after that, when it is positive, okay, we think of happy things. So it is your happy phase. So minimum point. Remember? So same thing as your quadratic function shape memory work. Okay. But I want to explain to you why this is the case. Okay. Let me just draw it out first. board. Okay, let's look at this very first column first. Okay, what I have as an example is the function y equals to negative 3x plus x cubed. If you just key into a computer, okay, to generate the graph for you, this will be how it looks like. Okay, it has a minimum point over here, right? Then if I were to differentiate your y over here, our dy over dx will be negative 3 plus 3x squared, and it actually generates for us this graph. Okay, my y-axis I label it as dy over dx because that is the function we're looking at. Instead of y, I have dy over dx over here. Okay, so when I compare these two graphs, I know that at the minimum point, we said that for stationary points, your dy over dx must be equals to 0. So therefore, your dy over dx value along the so-called vertical axis, okay, or the y-axis that you're familiar with, okay, the value is actually at 0 itself. Okay, at 0. So there is this matching over here. Okay, at this particular x value, so let's call it a. Okay, you will find that at a over here, this dy over dx value is actually equals to 0. Then we look at the gradient of the tangents on the left of a. On the left of a, we know that our tangents are all downward sloping. So your dy over dx value is going to be negative in value, which explains why on the left of a in this particular graph, you see that your graph values, your points itself are all below the x-axis. So your dy over dx is less than 0 over here. Okay, so it actually corroborates over here that this part is negative, so that's why the points lie below the x-axis. So likewise, on the right side of that point A, okay, we find that our tangents are all actually upward sloping. So your gradient is actually positive, which explains why over here, your dy over dx values are all positive. Okay, so it is a matching of this graph with this graph, okay, for us to then investigate the pattern about the second derivative. Okay. Any questions at this juncture? We understand how we get from here to here? Okay. So then after that, we look at the second derivative. We remember that every time we differentiate, we're looking at the gradient of the graph or gradient of the tangents itself. So second derivative, in this case, it actually gives the gradient of the tangents of these graphs. So if I look at all the tangents over here, they are always going to be upward sloping, which explains to us why, okay, that for any minimum point, okay, your second derivative will always be positive. So second derivative always positive for minimum point. Okay, so that's how we got this conclusion. Okay, and that's how we go about testing for second derivative. Questions? Okay. Similarly, when it comes to a maximum point, which is what we have in this case, at a particular point A, okay, where it is actually maximum, alright, again we know that your dy over dx value over here will actually be 0, which is what we have over here. Okay, then to the left of A, we find that our tangents are always upward sloping, positive in value, which explains why, okay, these points here, okay, are actually on top of the x-axis, above the x-axis, and your dy over dx are actually having positive values itself. Whereas over here, okay, your tangents are all downward sloping, okay, so our dy over dx values are negative. So that's why over here is all negative dy over dx values. Okay. Then looking at the tangents of the graph over here, they are always downward sloping. Okay. So that explains to us why that maximum point, okay, we actually have d2y over dx squared to be less than 0 because the gradient of this graph is downward sloping. Okay. Questions? So what I'm doing over here is to explain to you why, okay, we have our second derivative test in this manner. Okay, but of course, not necessary for you to know how to explain it, right? But I feel that you should reserve the explanation, okay, rather than knowing how to apply. Okay. Now, one very important thing is that when it comes to a point of inflection, we are not able to use our second derivative test to determine. You cannot say that second derivative test, the second derivative, when it is equals to 0, it gives you point of inflection. Not all the time, okay, it happens that way. Alright? So, if you find that your second derivative ends up becoming equals to 0, what you have to do is to use your first derivative test. Okay, so not conclusive. Use first derivative test. So that is the troublesome part. I'll show you an example later on. Okay? Questions? Derivative and when is it that we have to do first derivative? Usually in the question itself, it doesn't specify when you need what test you need to use. Okay, usually they don't say must use second derivative test, must use first derivative test. It is much more convenient, okay, to do second derivative test most of the time. Okay, especially when it comes to functions that are algebraic in nature. Okay. When later on, okay, when we go into chapter 15, where we are going to learn your differentiation of the trigonometric functions, exponential functions, and logarithm functions, right? Okay, that's where sometimes using second derivative test might be a little bit more tedious because you need to know how to differentiate all those complicated functions, okay, the second time. Alright, so you need to be familiar with both. Right? But usually second derivative test is much more straightforward and easier to use. Okay? So looking at try 4, we are given y equals to 2x squared minus 16x plus 27. We want to find the coordinates of the stationary point. So we first find out what is dy over dx. And that will be 4x minus 16. Since you're looking for a stationary point, so your first derivative must be equals to 0. So 4x minus 16 equals to 0, and we find that x will be equals to 4. Since you're trying to find the coordinates, we must find the y coordinate in this case. And that will land us with negative 5. Okay, so for negative 5 is the stationary point. Now we'll learn how to use our second derivative test to determine the nature. So in this particular example, it did specifically mention to use the second derivative test to determine the nature. Determine the nature of this stationary point using your second derivative test with our dy over dx being 4x minus 16. our second derivative in this case happens to become a constant value, that is 4. Okay? It is not all the time that your second derivative gives us a value itself automatically. Okay? Sometimes it can become a function, alright, for example 4x squared or something like that. So if it is a function, then you have to take this value and substitute it inside. Okay? Later on I'll show another example about that. Okay? So your second derivative happens to be equals to 4. You need to specify the second derivative second derivative value. So need to show us the value and then say that it is actually more than 0. Okay? So therefore, for -5 being positive will actually be a minimum point. Y equals to 6x to the power of 5. Okay, again, I want to find the coordinates of the stationary point and then also determine the nature. Right? Could I give you maybe about 3 minutes? Okay, work it out. Right? All the way until you find the second derivative value. Okay? Alright? So I want you to do all the way till you find your second derivative. Okay, then after that I will proceed from there. So give you about, okay, I think I give you about 4 minutes to work on it, okay? You're done, maybe for the faster one, you can give exercise 14.1 question 4 a try. Okay, you can give this a try. of you are done, such that you even went on to find that it is the point of inflection. That's great. To see and get is that the point, okay, the stationary point itself is at the coordinate 0, 0. Okay, and at 0, 0, your second derivative value should actually be 0 as well after substituting x equals to 0 into your second derivative. Okay, so as mentioned, when your second derivative is equals to 0, you have to use your first derivative test. You cannot conclude anything out of this. Okay, so in this case, you will find that it is a point of inflection. Okay, such that your first derivative test shows this. And we conclude that 0, 0 is a point of inflection. Okay? Are we all able to get this? Alright, now let's move on to look at and compare with exercise 14.1 question 4. Okay? This 14.1 question 4, right? Going through the same steps to find out the coordinates of the stationary point first. You will find that your first derivative is 30x to the power of 5. And then we find that your x coordinate will have to be 0 and your y coordinate will actually be 1. Okay, so the stationary point is at 0, 1 itself. Okay, then to determine the nature, we find out what is the second derivative. Okay, and that gives us 150x to the power of 4. At the stationary point, your second derivative would have a value of 0. Okay, and it requires us to use our first derivative test. And in this particular case, okay, our point 0, 1 is a minimum point. Okay, so through these two examples, 0, it does not always lead us to having a point of inflection. It can also lead us to a minimum point or even a maximum point. Okay, so you cannot take that kind of assumption that second derivative equals to 0 implies that it is point of inflection. Okay, so at this juncture, you may be wondering, if that's the case, might as well we use first derivative test all the time. You can if you like to, okay, no one is stopping you, unless of course the question specifies that you must use second derivative test or something like that. Okay, otherwise, okay, it's really up to you whether you prefer to use second derivative test first or just always use first derivative test. Okay, regardless, you need to still be familiar, okay, with the two tests itself, right? Because sometimes you may be required to use some of the tests. Okay, any questions? Right? Let's look at the final one. Okay, exercise 14.1, question 12. On this part I and part 2, you can give part 3 a try if you want to. Okay, but mainly I want us to focus on part I and 2 first. Okay, so would I give you maybe about 4 minutes to work on that? Making your life very difficult after you learn quotient rule. Okay, our denominator is only one item. x, so we can separate out the fractions, right? Okay, and then that makes our life much easier to do our differentiation. Agree? Okay, so no need to think about quotient rule. Okay. You can just that your quotient rule ends up being complicated.
Thank you, teacher.
Are we done? Okay, I have shown on the whiteboard the answers to part I and part 2. I hope you're all able to get that the stationary point is 327, and then 327 is a minimum point. Are we all able to get that using our second derivative test? Okay, so the good thing about second derivative test is that your working is definitely much shorter, and then you do get a more simplified way of doing things rather than doing first derivative test. Okay, so that's why usually we will still do second derivative test rather than jumping straight to first derivative test. Okay, I want to show you what if you didn't realize this simplification and you were to do quotient rule. Okay, if you were to do quotient rule, it's not that you cannot. Okay, just that it will look more complicated. Okay, for first derivative test, for first derivative, you may still find it more manageable. But when it comes to second derivative, that's where you may fall into careless mistakes and all that in terms of your calculation and simplification. Okay, so definitely more tedious when it comes to using quotient rule itself. Okay, although for second derivative test to be applied, actually also no need to go about simplifying. You can stick to here and then take your x value and substitute into it. You should get the same value 6 itself as well. Okay, so that is the challenge when it comes to quotient rule. Okay, I want us to know how to go about explaining in part 3 why the gradient of the curve is negative when x is less than 0. Okay, so let's try to understand what the question is trying to ask first. They're asking why gradient of the curve. Gradient of the curve would refer to your dy over dx. So the question essentially is asking, explain why dy over dx is negative, when x is less than 0. Okay, so this is the conclusion that I want to reach at. Okay, this is my conclusion. Okay, and what we are given as an information is your x is less than 0. Okay, so we have already found that dy over dx is equals to 2x minus 54x to the power negative 2. Okay, so if I were to continue over here, part 3. Okay, in other words, my dy over dx is just 2x minus 54 over x squared. Okay, I want to prove that dy over dx is less than 0. That means I want to prove that this is less than 0. Okay, it falls back to our inequality already. We are given that x is less than 0. Okay, there are two components in this expression. We have 2x, which we will know that it has to be less than 0. And then the other component is 54 over x squared. Okay, so 54 over x squared itself, x squared we will know that it is always positive. Okay, and then 54 over x squared will also be positive. Okay, so two parts are 2x less than 0, 54 over x squared is actually positive. Okay, so what does this mean? Okay, piecing them up together, we know that if 2x is negative in value already, I continue to minus a positive number, the entire thing will have to become negative, right? Okay, so you think about your numbers. If let's say this is negative 2, you continue to minus numbers like 3, 4, 5, 6. Even if minus 1 itself or 0.1, the entire thing will still remain as negative. Correct? It's our understanding of our numbers. Okay? This thing negative minus something positive continue to be negative. Okay? So therefore, your dy over dx will have to be negative. Okay? So no need to go about, going that long grandmother story. You just need to say that 2x less than 0 and 54 over x squared is more than 0, and conclude that dy over dx less than 0. Okay, so hence the gradient of the curve is negative when x less than 0. Okay, So example to help you imagine. Examples. On the left, if it's negative already, you continue to minus something positive, and result will always be negative. Okay, regardless of what numbers. Okay. Yep. Mindful of the time. Okay, homework for exercise 14.1. Okay, we will get 3, 7, 8, 10, and 14 as your homework questions. Okay, so that's in your textbook, page 56 to 57. Okay, sorry, let me just check my motion rule. I'll be not getting right. Okay. Right, any questions? Okay. I shall not hold you back. Please go on for your next lesson. Then I'll try to check your this as well. Sorry, you were saying? Oh, okay. Sorry, thank you. My bad. This one, I think we get the idea now. Okay, go for next lesson, yeah. Thank you for reminding me. Friday, 10? Because Thursday I'm not coming in. Will I be what? Will I be any other tomorrow I'm going to yeah.